Hi everyone, welcome to integrating rational functions using long division. Today that is what we're going to do. We're going to learn a new technique, but this technique also sometimes is in place of u substitution. So we're going to do a review u substitution. I'm just going to show you how u substitution works for this problem and then how integrating using rational functions works. So as you guys look at this problem, you have to start, we're going to do use substitution. So I want you to try it on your own, but the question, the hardest part normally is which one is our u. So both of these functions look very similar. If you take the derivative of this denominator, you'll get 2, so that doesn't really cancel out anything on the numerator. This derivative is 4, also doesn't cancel out anything on the denominator. So which one should you use? Well, a lot of times when we do problems where the degree is the same on the bottom and the top, we're going to end up having to actually do some division later on. And it's going to be a lot easier to split a numerator than it is to split a denominator. And so you want the denominator to be the piece that's less complicated. And so because of that, I'm going to choose my denominator to be u, because that guarantees that I only ever have one number on the bottom, and that is just like less complicated than having multiple. So u is going to be 2x minus 1. And again, just if you got that part, I want to see how far you can go on your own. So feel free to pause this and try this yourself. I'm just kind of setting up my problem. And then this part right here, what dx equals, is not going to cancel out this top function. But I am going to be able to figure out what x is with respect to u by just solving this equation for x here. Now I have all the pieces I need to change this rational function. Remember, rational function is just a function that involves division and has x on the bottom and x on the top. Now I have everything I need to change this rational function into a function with respect to u rather than x. So my integral sign is going to go here. I'm going to replace, I'll just do it one step at a time. I'm going to replace my denominator with u, and then I'm going to replace dx with du over 2. And then I'm going to pull that 1/2 out in front, so I have this now. And then I'm going to now plug in u plus 1 over 2. And for u, can't forget about my 1/2 out in front. And then I'm just going to kind of clean it up as much as I can before I actually take the antiderivative. So to do that, these cancel out and that becomes a 2, so I'll have 2u plus 2 plus 4 on the numerator. I'm going to keep going. 2u plus 6 over u du. I'm going to stop there real quick. Just going to take a second and check my work. Everything looks good to me. So now we only have things with respect to u, but we all still have a quotient. And like we said, there's no quotient rule for antiderivatives. And so one way to avoid the quotient rule is to actually do the quotient. So I'm going to go ahead. I can split my numerator. I can never split a denominator. It doesn't work that way. But I can split the numerators. This would be 2u over u plus 6u du. And then I'm just going to simplify, so that'll become 2 plus 6u to the negative 1 power du. And now it's in a form where I can take the antiderivative. Everything's in exponential form, nothing's in a fraction, and then it's just addition. So that's going to be 1/2 times 2u plus 6u to the, what is this again? Oh, you actually didn't need to do what I did, because this 1 over x is just the natural log. So this is actually, I didn't even recognize this, but this is actually going to be 6 natural log of x, and then remember of u plus c. And then now I can go ahead and plug everything back in for u. So again, u was 2x minus 1 plus 6 natural log of 2x minus 1, and then I just have to make sure I have my c, and that is the answer to the first one. There are ways, obviously, you guys could simplify that if you would like to, but I'm not going to make you simplify that down. I just want to see how many problems we can get to during this time. So that is the answer for the first one. Okay, we're gonna start same example, but a separate method. And I'm sorry if this cut is weird because my iPad overheated yesterday, so I'm starting over this example. But essentially what we're gonna do for this one is we're going to still solve it, but we're not gonna use substitution this time. We're gonna use long division. And so just to recap of how do we do long division, I'm just gonna give you a random problem over here. I'm actually gonna give you two problems. We're gonna start with, we'll just do 760 divided by 5, okay? So just draw this maybe over to the side. So this is just how we do long division, okay? What you'll do is you'll take this first number, 5, right? 5 is going into 760, and you'll think, how many times can 5 go into 7 without going over? The answer is 1. So then you'll put a 1 over the 7, and then you'll do 5 times 1, which is 5, and you'll subtract, and you'll get 2. Next, you'll pull down the 6, and you'll think, how many times does 5 go into 26 without going over? Answer's 5. And then 5 times 5 is 25. So you'll get 1, and then you'll pull down the 0, and you'll pull down until you're out of numbers. 5 goes into 0, or I don't know what I'm saying. 5 goes into 10 twice. And then 5 times 2 is 10, and I'm done, and there's no remainder. And so that's how you do long division. 760 divided by 5 is 152. Real quick, let's look what happens if I do 761 divided by 5. So obviously the first part of this problem is going to be pretty much the exact same. So I'm going to go through it kind of quickly. Okay, so I get here and I am left over with 1. There's no more numbers to write down. So there's two things you essentially can do here. You can write 152 remainder of 1, right? Or you can write 152 1/5. And the reason that it's 1/5 is because 1/5, right, of 5 can go into 761. So part of 5 can go into 61, one part of the 5, right, but not all 5 parts. And so that's why it's 1/5. So just like kind of keep that in your head as we do long division here. So with this problem right here, we're not going to use substitution. So we did in the last problem, but obviously it wasn't great. It's kind of ugly. I'm not going to promise you this one's not also going to be ugly. And we actually will have to use substitution down the road, but it will be easier use substitution. But essentially what we're going to do is the two methods if you get a quotient in antiderivatives is you can either use substitution or you can try to get rid of the quotient by actually dividing. And so what I'm going to do here is I'm going to do 4x plus 4, and I'm going to try to divide it by 2x minus 1. Now this is polynomial long division is something that you should have done in pre-calculus. So this is just like a reminder of that. So what I'll do is I'll think, how many times does 2x go into 4x? Answer is 2. And so then I will multiply this whole expression by 2, and I'll get 4x minus 2. And just like in the last problem when I was doing like long division like we did in elementary school, the next thing you'll do once you get that factor is you'll subtract. So I'll subtract everything, and that will give me 4x minus 4x, which is 0, and then 4 minus negative 2 is 6. Because remember, if you subtract the negative, you get, If you subtract a negative, you get a positive. Well, not necessarily positive, but you add, right? Okay, so here's our answer. We are getting that 2x minus 1 goes into 4x plus 4 twice, but it has a remainder of 6. And so the way that you're going to write this is just like how you wrote the other one. You'll write 2, and then you'll write plus 6, because that's your remainder. And it was 6 pieces out of the whole, which is 2x minus 1. Just like we had 1 piece out of the whole, which was 5. And so that is actually what this expression right here is equivalent to. So 2 plus 6 over 2x minus 1 dx. So that is where we're going to start, and that's going to help us find the antiderivative. And so should have written a couple things smaller over here, but I'm going to go ahead and I actually am going to separate this into two integrals, okay? I'm going to separate this into the integral of 2 and the integral of this part. The reason I'm going to do that is because the integral of 2 is a really easy number to find. It's just going to be 2x, but this part over here is actually going to be a little trickier. So that's what I'm going to get from there. I know that the integral of 2 is 2x, right? And then 2x plus c, but there's just only going to be 1c, so I'll add it later. But the question is, okay, well, what do we do with this here? Because this is still a quotient. And so what you still have to do here is you do still have to use substitution. I'm very sorry, but it's a lot easier use substitution. I'm kind of running out of space, so I'm just going to do this over here in the corner really small, but I'm going to choose u to be the more complicated function or the denominator. Normally, like it's either the denominator, the thing inside the function, or the most complicated. So it's going to be 2x minus 1 and the derivative of that is 2. And then if I were to solve for dx, I'd get du over 2 equals dx. And so I will have 6 over u times du over 2. And when I simplify that up, I'm going to get 2x plus, this part right here simplifies to 3. So that's going to be 3 over 1 over u du. And this, you're going to have to, long division, you're almost always going to have a logarithm in your final answer. The only reason you wouldn't have a logarithm is if there was no remainder. But if there's a remainder, you're like literally almost always going to have a logarithm. So the antiderivative of 1 over u is the absolute value of the natural log of u. Now I'm going to add a c because I have to have it somewhere. And I'm almost done, but obviously you might see here there's a mix of x's and the mix of u's. Our final answer needs to just have x's, and so my final answer is this. My u was 2x minus 1, and that was plus c, and this is our answer. And so honestly, like, still not like a super fun and easy problem, but like if you look about the amount of work I did here versus the amount of work I did in this first problem, I would prefer to use this bottom problem. It also looks worse because we did this elementary school long division over here. So this one is a really good method to use when you have polynomials and the numerator has a higher degree than the denominator. So let's go ahead and go look at another problem. Eventually you won't even have to use substitution. You'll kind of just like recognize the pattern. So I'm going to do long division here. So we're not doing u substitution because u substitution is just kind of a pain in the butt. And it did work in that first one, but it might not work in all of them. And so you just have to keep that in mind. So I'm going to do 3x minus 1 divided by 3x squared plus 5x plus 3. So I just think, how many times does 3x go into 3x squared? It goes in x times because 3x times x is 3x squared. So I'll get 3x squared here, and then I also have to do the -1 times the x, so it'll be a -1x. And that's my first step, and I subtract, because you always subtract when you're doing long division. So if you do it correctly, these terms should cancel out, the 3x squared and the 3x squared. 5x minus a -x is a positive 6x, and then I'm going to carry down my 3 plus 3. We actually have to keep going because the last time we only had one number left, but we had 2 terms, and you can't put 2 terms into one term, obviously, but this time we actually do have 2 terms going into 2 terms, so we can keep going. So I'm thinking, how many times does 3x go into 6x? The answer is twice. So I'll do 6x minus 2, and then I'll subtract. The 6x's will cancel out, that was the goal, and then 3 minus -2 is a 5. And now I have nothing else to work with, and so my answer is going to be x plus 2, and then we have this remainder of 5, but it's 5 pieces out of the whole, which is 3x minus 1. And so this expression here gets simplified down to x plus 2 plus 5 over 3x minus 1 dx. And I'm just going to go ahead and take the antiderivative of the parts that are easy to take the antiderivative of. So for example, antiderivative of x is x squared over 2. The antiderivative of 2 is 2x. And then this part over here is going to cause me the most trouble, so I'm just going to put it there. But I'm just going to get those like easier parts out of the way. So again, for this part right here, I'm going to need to use substitution because I still have a quotient. And so I'm just going to do this over to the side. It's literally like it's the exact same thing as the last one, almost just like slightly different numbers. So u equals 3x minus 1, du dx equals 3 because that's the derivative. Solve for dx, and I'm going to get this, right? And now I'll just plug in. So I'm not going to change anything that's outside of the integrand because that's not involved right now. I'll get 5 over u times du over 3, and then this becomes x squared plus 2x. You should be really neat. I'm going to pull out 5/3 because they're just a coefficient. I get 1 over u du, and then it'll be x squared over 2 plus, oh, I gave you two slots here because of how much work, like how much space it is, so that's why that's there. So sorry, I'm just letting you know that now. Plus 5/3, and then the antiderivative of 1 over u is the absolute value of the natural log. Oh, but I need to put u there. And then I'm going to make sure I add my c. And then finally, I need to make sure that my final answer just has x's in it because I was originally working with x's. And so my u is 3x minus 1. And so if you get the hang of that, you really just like don't even have to do all that side work. You just like kind of recognize that that's always going to occur. And so that's nice. Okay, one more problem. This next one is a nice problem, and you'll see why in a second. So, same idea. I am going to do my long division. Another reason why you should use long division here is like if say you were to choose for this problem, like I would probably choose this to be u, but if I took the derivative of this, this would become 6x squared, and then this would be 6x and this would be 3, and that's just not going to cancel out x minus 2. So using u substitution here, like on a big scale, obviously we've been using u substitution slightly as we go along, but using it on a big scale is just not going to get you anywhere. So how many times does x go into 2x cubed? The answer is 2x squared. So then this will be 2x squared minus 4x squared. Subtract everything. Cancel. This becomes 1x squared. Drop down the minus 3x. I'm not worried about the 2 yet, but I can technically drop it down. How many times does x go into 1x squared? The answer is x times 1x squared minus 2x. Subtract. I get negative 1x plus 2. How many times does x go into negative x? That's a negative 1 time, so I'll get negative 1x plus 2, subtract, that equals 0. And so this one's super nice because there's no remainder. And so this actually just simplifies to 2x squared plus x minus 1 dx. And then, man, this isn't even that bad of a problem from here. I just take the antiderivative. So the antiderivative of 2x squared is 2x cubed over 3. And then the antiderivative of x is x squared over 2. And then the antiderivative of negative x is, or negative 1 is negative x. And then make sure I add my c because this is an indefinite integral. And that is our answer. So we are done. Hope you enjoyed doing long division. I started off and I made it as hard as possible, and then I hope it felt easier as you went. Goodbye.